Hello, my name is Dr. Garuma Abdisa, and in this tutorial we will cover refraction of light and Snell's law. Refraction of light. The change in the direction of a ray as it passes from one medium to another is called refraction. Light travels at different speeds in different media, and consequently light is refracted. Assume, for example, this container contains some water, and as light ray passes through this water coming from the air, it is refracted. For example, if you place some straight object like a pencil in a water in a container such as this, it appears as if it was broken. And that is the demonstration of the refraction of light. So this angle is angle theta 1, and this angle is angle theta 2, and the upper medium, in which case I am considering to be air, that is medium 1, has a refractive index of n1, and the second medium, in my example, is water, has refractive index n2. N is the index of refraction, and n is defined as the speed of light in a vacuum divided by speed of light in that particular medium. N is simply c over v, because c is the speed of light in a vacuum and v is the speed of light in the specific medium we are talking about. N1 is c over v1, and N2 is similarly c divided by v2. Assume this construction, and from this, cosine of 90 degree minus theta 1, that is this part, I'm considering triangle ABC, that is this triangle making 90 degrees there, because these two rays are coming in. When ray 1 is just over point A, the second ray, ray 2, is at point C. During the same time interval that ray 1 travels from A to D, in the same time ray 2 travels from C to B. So the distance AD and the distance CB are traveled within the same time interval. And now cosine of 90 minus theta 1 is simply sine of theta 1 if you expand cosine. So cosine of 90 minus theta 1 is adjacent, which is this BC, divided by the hypotenuse, which is AB. Similarly, cosine of 90 minus theta 2, that is for this one, which is adjacent, divided by hypotenuse, which is AD, divided by AB. And upon simplification, cosine of 90 minus theta 2 simplifies to sine of theta 2, cosine of sum and difference. If we take the ratios of this sine theta 1 and sine theta 2, we will get sine theta 1 over sine theta 2 is equal to BC over AB divided by AD over AB, which reduces to BC over AD. And I have told you that this distance BC is traveled during the same time as this AD and BC, but they are in different media. AD is traveled inside of medium 2, while BC is traveled inside of medium 1. They will have different speeds, V1 and V2. But both of them happened during the same time interval. So for BC we write V1t, and for AD we write V2t, which simplifies to V1 over V2. And this ratio, sin theta 1 over sin theta 2, is now written as V1 over V2, but V1 is C over N1, and the V2 is C over N2, which reduces to N2 over N1. Or N1 sin theta 1 is equal to N2 sin theta 2, which is called Snell's law. So, in short, Snell's law is that if we have this angle to be theta 1 and this angle to be theta 2, the upper medium is medium 1 having refractive index n1, and the lower medium is medium 2 having refractive index n2. Snell's law says that n1 sin theta 1 is equal to n2 sin theta 2. n1 is the refractive index of medium 1, n2 is the refractive index of medium 2, and theta 1 and theta 2 are simply angles of incidence and angle of refraction respectively. So in words, Snell's law is, as light crosses a boundary from one medium to another, the product n sine theta remains constant, or n1 sine theta 1 is equal to n2 sine theta 2 is equal to n3 sine theta 3, and so on. Remember that the angles of incidence and refraction are always measured relative to the normal to the boundary. So the first case, case 1, is whenever n2 is larger than n1, the refractive index of medium 2 is larger than refractive index of medium 1. So n1 sine theta 1 is equal to n2 sine theta 2 is our Snell's law, and we can rewrite this one as sine theta 1 is equal to n2 over n1 times sine of theta 2, together with the condition n2 is larger than n1, we can write as sine theta 1 must be larger than sine theta 2 in order for this situation to hold true. So, in other words, theta 1 is larger than theta 2. The beam bends towards the normal. If n2 is greater than n1, the beam bends towards the normal. The second case, if n2 is less than n1, n1 sine theta 1 is equal to n2 sine theta 2 is our Snell's law. Sine theta 1 can be written as the ratio of n2 over n1 times sine of theta 2, and because n2 is less than n1, we can write sine theta 1 is less than sine theta 2. And this implies that theta 1 must be less than theta 2. So, the beam bends away from the normal whenever n2 is less than n1. A ray traveling from a denser, example like water or glass, to a less dense medium like air, the beam bends away from the normal. A ray traveling from a less dense medium like air to a denser medium like water or glass, the ray bends towards the normal. If theta 1 is equal to 0, that is the normal incidence, the Snell's law equation has the solution that theta 2 has to be 0 regardless of what value of n1 and n2 have. In general, light that is incident perpendicularly to a surface between one medium and another does not change direction as it enters the second medium. Now let us see total internal reflection. If this medium 1 has a refractive index n1 and another medium 2 has refractive index n2, and whenever light passes from medium 1, that is from the lower medium to the upper medium n1 to n2, it passes unrefracted because of the situation that we have seen a while ago. So perpendicular rays do not change direction always. And if this is a normal, if instead light ray is going this way, from medium 1 to medium 2, it is partly refracted and partly reflected. This angle is called theta 1 and this angle is called theta 2. Likewise, if we have another normal here, now we are increasing the angle theta 1 because this angle theta 1 is now only this much, but now I'm increasing angle theta 1 to that much. It's once again both partly reflected and partly refracted, and these are theta 1 and theta 2. As I do so, these angles are increasing, theta 1 and theta 2. I'm increasing the angles. Thirdly, if I make another normal here, if I again further increase this angle of incidence theta 1, at a certain point what happens is this ray lies over the surface or over the boundary between the two media. So this angle is called the critical angle. That is the angle at which the angle of refraction becomes 90 degrees. So the refracted ray parallel to the surface at theta c. So at this, whenever the incidence angle becomes theta c, now the refracted angle becomes 90 degrees. That angle for which the angle of refraction becomes 90 degrees is called the critical angle. To have total internal reflection, one very important condition is that N2 must be less than N1. For example, medium 1 can be like water and the medium 2 can be air. So the refractive index of this media, the medium here, that is the refractive index of the second medium, must be lower than the refractive index of the first medium. Example, medium 1 can be water, having a refractive index of 1.33, and the second medium can be air, refractive index 1. Critical angle is a limiting angle for which the refracted ray is parallel to the surface, that is theta 2 is equal to 90 degrees. If theta 1 is greater than theta c, that means if we further increase this angle, no refracted ray will happen. That is, all incident ray is reflected back to water. The situation of having all the incident rays being reflected back into the medium 1, that is in our example water, is called total internal reflection. Snell's law, N1 sin theta 1 is equal to N2 sin theta 2, gives us the value of the critical angle for any pair of media. N1 sin theta c, that is a critical angle, is equal to N2 sin 90 degrees. That is N2 times 1, which is equal to simply N2, and sin theta c becomes N2 divided by N1, or the critical angle is simply the sine inverse of the ratio of N2 to N1. It is very important to remember that total internal reflection can occur only when N2 is less than N1. No angle has a sine greater than 1. And so, sine of theta c, sine of the critical angle, has no solution unless N2 becomes less than N1. So here are the conditions for the total internal reflection. The first is angle of incidence must be larger than the critical angle theta c. Secondly, the refractive index of N2 must be less than N1. If we have N2 and N1 here, so as light goes from N1 toward this N2, it will be totally internally reflected. It is reflected within the first medium itself. It has not passed to the second medium. It has not refracted, because this angle is above the critical angle. Because in this case I is simply larger than theta c, which is the critical angle. Total internal reflection occurs when light travels from denser, example water or glass, to a less dense medium, example air. Example 1. Calculate the speed of light in water, n 1.33, and the speed of light in a vacuum is 3 times 10 to the 8th meter per second. Solution, V is C over n, which is 3 times 10 to the 8th meter per second, divided by 1.33, which is 2.26 times 10 to the power of 8 meter per second. So the speed of light in water is simply 2.26 times 10 to the power of 8 meter per second, which is lower than speed of light in air or speed of light in a vacuum. Second example, if light is passing from air towards water, being refracted, as it is indicated here, and if the angle of incidence I is 45 degrees and the refractive index of water is given to be 1.33, and find the angle of refraction R. The solution is n air times sine of incidence I is equal to n water times sine of refraction R. By directly substituting what we have, that is refractive index of water to be 1.33 and that of air to be 1. Remember that the refractive index of air is 1. And by directly substituting, we get R is equal to the sine inverse of sine 45 degree over 1.33, which will give us 32.11 degrees. Third example, the refractive index of glass is 1.5. At what angle of incidence should a ray of light strike the interface between air and the glass in order for the refracted ray to travel along a path at an angle of 30 degrees to the normal line? As a solution, we have, this is the arrangement of what is already given in a statement. Light is traveling from air toward this glass. N air sine of incidence I is equal to n glass sine of refraction R. For glass, we have the refractive index to be 1.5, which is already given in the problem. And for air, we already have n to be equal to 1. And it's given that r is 30 degrees and we are required I now. So directly substituting everything we have, we can write this line, and from which I is simply the sine inverse of 1.5 times sine of 30 degrees, which reduces to 48.6 degrees. The fourth example, calculate the critical angle for a glass-air interface, given that the refractive index for glass is 1.5. This is a demonstration of what is given. Light is passing from glass to air. We are required to calculate the critical angle, that is this theta c, and this have to make 90 degrees. That is what is simply meant by being a critical angle. So for glass, n1 is 1.5, and for air, n2 is 1. We have the critical angle, which is sine inverse of n2 divided by n1, which is sine inverse of 1 over 1.5, and theta c is simply 41.8 degrees.